we're now going to look at a class of groups that are going to be useful to us to keep in mind as we understand more about algebra and the algebraic structures that we're studying. And these groups are going to be denoted the following way, as Z mod NZ. That's how we're going to read this. Z mod NZ, where that slash there is mod, and we're going to see a little bit of why we use this. This is going to be related to congruence modulo a number that we looked at when we were looking at equivalence classes and equivalence relations. So we're going to let Z mod NZ be as a set, the set of equivalence classes of X, where X belongs to Z, where here these equivalence classes are modulo n. So these are the equivalence classes of integers modulo some positive integer n that we've been looking at before. Now we're going to claim that Z mod NZ is a group under addition. Now when we do this, we have to specify, well, what do we mean by adding two equivalence classes? If I take an equivalence class Y and add it to an equivalence class of X, then the natural thing to do here is to look at the representatives of these equivalence classes. These equivalence classes are sets of integers, but they have representatives. The representative of the first class is X, and the representative of the second class is Y. And X and Y are both integers, and we know how to add integers. Addition is a normal operation that we could do with X and Y. So what we're going to do is we're going to try to define the sum of two equivalence classes to be the equivalence class of their sum. Now, when we do this, we have to be really careful. We have to, before we check any of the group conditions, properties, we need to make sure that this operation makes sense, is well defined. In particular, we need to make sure that if I choose a different representative for, say, the first equivalence class and a different representative for the second equivalence class, then we still wind up with the same equivalence class at the end. Now, we can do a couple of examples to see why we might believe that should be true. Let's suppose that, let's take a sub-example here. Let's look at the equivalence classes modulo 6. And in this group, if I take the elements, the equivalence class of 1 and the equivalence class of 5, and add them together by this definition above, I would get the equivalence class of 1 plus 5, which is the equivalence class of 6. However, I could also look at what happens if I take the equivalence class of 7 and the equivalence class of, let's say, 17. Now, notice that the equivalence class of 1 is the same as the equivalence class of 7, and we know this because 1 is congruent to 7 modulo 6. Similarly, 5 is congruent to 17 modulo 6, and therefore the equivalence class of 5 is the equivalence class of 17. And under this definition of addition, the sum of the equivalence class of 7 and the equivalence class of 17 should be the equivalence class of 24. Now, we started with a pair of equivalence classes, added them together. Then we took those same equivalence classes but written a different way and added them together, in order for things to make sense, we should get the same equivalence class at the end. And you'll see that in the first case, we got the equivalence class of 6. In the second, we got the equivalence class of 24. 6 and 24 are, in fact, congruent modulo 6, and therefore these two equivalence classes are the same. So what we've seen is just a simple example to show that there's a chance that this addition makes sense here. Now, there's a general concept and definition that we are working with here that we want to address and make very precise. So definition 22 says that a rule which takes an element of a set A to an element of B, and this rule I'll denote it as F, is well defined if whenever A1 equals A2, f of A1 equals f of A2. So this is saying that if an element of A is given and another element of A is given, which is actually the same element as the first one, and we apply the rule F to the two of those things, then we should get the same result at the end. We should get the same result over in B. Now, this looks almost trivial. Wouldn't this always be the case? And whenever we're dealing with a function, it certainly is. In order for some rule to be a function, it has to be well defined. But we can come up with rules that go from an element of A to an element of B that aren't well defined. So for an example, or really a non-example of this, let's let F be a rule that goes from the set of rational numbers to the set of integers be defined in the following way. F of P over Q is equal to P plus Q. Now, every rational number can be written in the form P over Q, and so if I have a rational number written in the form P over Q, I can apply this rule F to it to get an integer P plus Q over here. However, this F is not well defined, because if we take F of 1/2, we get 3, but if we take F of 3/6, we get 9. But, of course, 1/2 and 3/6 are equal to each other. What's going on here is that the single rational number 1/2 has many different ways that it can be written. In particular, it could be written as 1 over 2, and it could be written as 3 over 6. And when you have multiple ways of describing the same object, you have to be very careful when you define a function in terms of that representation. In this case, our problem is that we are using the representation P over Q for a rational number, but that isn't unique. There are lots of different ways of writing down a rational number this way. Now, it's important to note that just because we've written down a function in terms of the representation P over Q, that doesn't by itself make the function undefined, or ill-defined, rather. It could still be well-defined. We would just have to show that if P over Q and, say, R over S are two different ways of describing the same fraction, that the result we get out of it after applying the rule F gives us the same thing. So let's see how this is applied as we go to show that the addition we've just described on the set Z mod NZ is well defined. So theorem 23, addition on Z mod NZ is well defined. Now, for a bit of notation before I begin the proof, we are going to be working with these equivalence classes in these sets Z mod NZ very often, and we're going to want a slightly more efficient notation for this. We may write x bar, x with a bar overhead instead of the brackets around x. And this x bar is going to mean the same thing. It's still going to mean the equivalence class of x, but we're going to use it so often that we want to establish it right away. So let's look at the proof of theorem 23. So here's how proving well-definedness of addition has to go. First of all, we're going to take two things in Z mod NZ, so I'll call them x bar and y bar, and let's let x prime bar and y prime bar be in Z mod NZ such that x prime bar equals x bar and y prime bar equals y bar. So now x prime, y prime are a whole bunch of integers, and we're looking at their equivalence classes. This condition that we have here where x prime bar equals x prime means that x prime is another representative for the equivalence class of x. It means that it's just another way of writing down what the equivalence class of x is. So now we have that if we want to add x bar and y bar together, that's going to give us x plus y with a bar over the whole thing. And x prime bar plus y prime bar is going to be x prime plus y prime bar. We need to show that x plus y bar equals x prime plus y prime bar. We need to show that no matter what representative we choose for the two elements we're adding together in this set, that we get the same result out of it. So x plus y bar is equal to x bar plus y bar. We need to show that. In order to prove that an equivalence class of x plus y is equal to the equivalence class of x bar plus y bar, this is equivalent to saying that x plus y is congruent to x prime plus y prime mod n. So two representatives have the same equivalence class if they are congruent under the original equivalence relation, in this case congruence mod n. Now, we know some things already about x bar, y bar. So we know that x prime is congruent to x mod n, so that means that there exists some p, an integer, such that x minus x prime equals pn. Because x and x prime are congruent, that means that their difference has to be divisible by n. Since y prime is congruent to y mod n, there exists q such that y minus y prime is equal to qn. Therefore, this means that if we want to compare x plus y and x prime plus y prime, we can do that in the following way. X plus y minus x prime plus y prime is equal to x minus x prime plus y minus y prime. But we know that x minus x prime is equal to Pn, and y minus y prime is equal to Qn, so that means that P plus Q times n is equal to x plus y minus x prime plus y prime. So this means that x plus y is congruent to x prime plus y prime mod n. And that's what we wanted to show. So what this theorem is showing is that when we're working with equivalence classes mod n, that if you take two things that are congruent and another two things that are congruent and add them together in pairs, the two results that you get are going to be congruent, modulo n. So this theorem shows that the addition that we wanted to describe on Z mod NZ is well defined. It means that it makes sense at all, which is the first thing that you need to check whenever you are looking at a group that has representatives where each element of that set can be written in multiple different ways. You need to make sure that that the way that you write down your element doesn't change how you get to your operation, what your operation gives you when you apply it to those elements that you've written differently. So that's the first thing that we need to show. The good news is that once we have this, once we know that addition on Z mod NZ is well defined, the rest of the group conditions are very easy to check. In fact, they are going to basically all come from the fact that Z itself is a group under addition. And therefore, Z mod NZ, equivalence classes involving integers, are also going to be a group under addition. So let's check that Z mod NZ with addition is a group. So first, associativity. We want to check that if we take x bar plus y bar plus z bar, we want to make sure that that equals what we get when we take x bar plus y bar plus z bar. Well, let's go ahead and do this. Y bar plus z bar is y plus z bar. That's part of the definition. And x bar plus y plus z bar is x plus y plus z bar. Going the other way, we have x plus y bar plus z bar, and that's going to give us x plus y in parentheses plus z bar. And these two are equal since x plus y plus z equals x plus y plus z. Basically, because addition is associative on the integers, it's also going to be associative on this set Z mod NZ. All right, next we need an identity. Well, we can start thinking back to the same thing. What's the identity for addition on Z, on the integers? The identity for addition on the integers is 0. And therefore, we can say, well, let's try the identity, the equivalence class of the identity. So 0 bar is, in fact, the identity. Because if I take any x bar plus 0 bar, that's x plus 0 bar, which is just x bar, and similarly in the other direction. All right, now what about inverses? Again, we can look at what happens in x. So the inverse of x bar is, well, we can think back to what's the inverse of x, an element x in the integers under addition. The inverse of x under addition is negative x, the opposite of x. And the same thing is going to be true here when we go to the equivalence classes. So the inverse of x is the opposite of x. We can see this by seeing that x plus the equivalence class of negative x is equal to x plus negative x, which is the equivalence class of 0. And finally, this shows that we, in fact, have a group, but we also show that this is an abelian group, because if I take x bar plus y bar, that's the same as x plus y bar, but because addition is commutative down in Z, x plus y bar is equal to y plus x bar, which is y bar plus x bar. So in fact, addition in this group is commutative. We have an abelian group. So let's see a quick example, because we've been working in the abstract here. Let's take a look at something specific. Let's look at Z mod 6Z. This is going to be the equivalence class, the set of equivalence classes of elements of Z modulo 6. Now, it's easy to write down a complete set of elements here. We're going to get the equivalence class of 0, equivalence class of 1, equivalence class of 2, 3, 4, 5. But the equivalence class of 6 is actually the same as the equivalence class of 0. And that's because 0 and 6 are congruent mod 6. The equivalence class of 7 is equal to the equivalence class of 1. Equivalence class of 8 is the equivalence class of 2, so on and so forth. And so in particular, we see that Z mod 6Z has exactly 6 elements. The equivalence class of 0, equivalence class of 1, 2, 3, 4, and 5. So we can look at, for instance, the equivalence class of 2 and ask, what is its inverse? So we want 2 bar plus something to equal 0 bar. Now we could just go ahead and use the inverse that we proved exists from last time, 2 plus negative 2 bar equals 0 bar, and this is perfectly correct. I want to emphasize that negative 2 bar, the equivalence class of negative 2, is a perfectly good way of writing down an equivalence class in this set. We, as humans, like the equivalence classes 0, 1, 2, 3, 4, 5, because they're all non-negative, and they're the smallest non-negative ones that work. But mathematically, there's no reason to prefer this over the equivalence class of 6, 7, 8, negative 3, 10, and 11. That's also a perfectly good way of writing down the set of equivalence classes in Z mod 6Z. So mathematically, this is perfectly fine. We can leave it here. But for our intuition, for our understanding, it is often helpful to write things down in terms of sort of standard representatives for us. And so the equivalence class of negative 2 is also the same as the equivalence class of 4. So in fact, we get that the equivalence class of 2 and the equivalence class of 4 are inverses of each other, because if we add the two together, we get the equivalence class of 0. Now, why is that the equivalence class of 0? Well, because it's the equivalence class of 6, and 6 is congruent to 0 mod 6. In fact, any multiple of 6 belongs to the equivalence class of 0. So this is this is basically how we go about doing this. We will, in a little bit, develop an addition table, which can help us to understand the structure of groups that we look at. All right, so next, let's try asking what other operations we could try doing with Z mod 6Z. So let's ask, what about Z mod NZ with multiplication? So here we have to define multiplication again, and we're going to define it in the natural way. The product of two equivalence classes, X bar and Y bar, will be the equivalence class of the product XY. Now again, we can show that this is well defined. It is well defined, and that's a good exercise to go through to prove that if X bar equals X prime bar and Y bar equals Y prime bar, then XY bar is equal to X prime Y prime bar. So we can show that it's well defined. I'm going to skip that for a second. We can go through. We can see that associativity holds since associativity holds since multiplication is associative on Z, basically exactly the same argument we had for addition. We have an identity. The identity element here is going to be, again, the equivalence class of the identity, of the multiplicative identity on Z. And Z did have a multiplicative identity, but you'll remember that we had a problem with inverses before. And we're going to have an issue with inverses here. So inverses don't always occur. In particular, the element 0 bar has no multiplicative inverse. Because if I take 0 bar and multiply that by any b bar, that's always just going to be the element 0 bar, which is not the same as 1 bar. Unless n equals 1, which is a very, very trivial situation where the element, where the set Z mod NZ has only one element in it. So this means that Z mod NZ with addition does not have inverses. Now, the last time we ran into this, we tried to fix this by doing a couple of things. One of the things we did is we tried just getting rid of 0. So we can ask, well, is it good enough to just remove 0 or 0 bar? And an example will show that, unfortunately, the answer is no in general. So let's I'm just going to go ahead and let G be the set of all elements modulo 6, equivalence classes modulo 6, other than 0. So all these equivalence classes are modulo 6. So now G with multiplication is not a group. And the reason it's not a group is because now it's not closed under multiplication. This is because if I take the element 2, multiply it by the element 3, that would be the element 6, the equivalence class of 6, which doesn't belong to G. So G is not closed under multiplication. So it looks like we've got a bit of an issue here, and we have to be more careful with things. However, all is not lost. We actually have another more sophisticated way of constructing a group with multiplication. We just have to be even more restrictive about what elements we allow in. So let's take this. So for any positive integer n, we want to let z mod n z cross. We're going to use this notation up here. This cross is meant to sort of suggest multiplication. This is going to be the set of things that are going to work with multiplication. It's going to be the set of all equivalence classes of x under congruence mod n, but we only want to consider the elements that are relatively prime to n. So we're going to consider the set of all equivalence classes modulo n, where the representatives are relatively prime to n. So, for example, if I take z mod 6z cross, that's going to be the set 1 bar, then not 2 bar, because 2 is not relatively prime to 6. They have a common divisor of 2. 3 and 6 have a common divisor of 3. 4 and 6 have a common divisor of 2. And 5 and 6 are relatively prime. So z mod 6z cross is just the set 1 bar and 5 bar. For a more complex example, we can look at z mod 15z cross. And this is going to contain 1 bar, 2 bar, not 3 bar, 4 bar, not 5 bar or 6 bar, but 7 bar, 8 bar, not 9 bar or 10, but 11 bar, not 12, 13, and 14. So it's the equivalence classes of all numbers that are relatively prime to whatever n you started with here. And we're going to define multiplication the same way. And an exercise is that z mod nz cross with multiplication is a group. So this is another good example of a multiplicative group that behaves a little bit uniquely. It's not something that we encounter in a lot of other places before now, but these turn out to be quite useful for what we want to do later. So to check that this is a group, you've got to do a few things. You have to show that multiplication is well defined. You have to show that it's closed. You need to show that if I take two elements in this z mod nz cross and multiply them together, I still get something that's in z mod nz cross. In other words, if I take two things that are relatively prime to n and multiply them together, I should get another thing that's relatively prime to n. You need to show that multiplication is associative. That one's not so hard. That just comes from associativity on the integers. You have to show that it has an identity. Now, notice that both of the examples we have here include the element 1 bar, which was our candidate for identity before. You need to make sure that no matter what n you choose, you still have this 1 bar element inside your group. And you need to show that for every element, there's an inverse to it. So you need to show that if I take something in z mod nz cross, and then there's something else in z mod nz cross that you can multiply by to get to 1. This is possibly the most difficult part of the exercise. So we can just go and confirm that that's the case, because it doesn't look immediately like necessarily it should be. So for instance, if I take 2 here in z mod 15z, I want to find some other element of this group that I can multiply by 2 bar that will give me the identity, which is the equivalence class of 1. And I can notice that, oh, well, if I multiply it by 8 bar, their product is going to give me 16 bar, which is, in fact, the equivalence class of 1, because 1 and 16 are congruent mod 15. Their difference is divisible by 15. And so then we can check some other ones. So 4, for instance, this one's a little bit different. 4's inverse is itself, because 4 bar times 4 bar is 16 bar, which again is 1 bar, and we can go so forth and so on. So given any given any element of Z mod 15Z, you should try and show that there's some other element that multiplies by that to give you the equivalence class of 1. And then see if you can prove that the same thing is going to be true for any n. All right, we're going to leave this here for a second, and we're going to move on to some more general properties of groups that some of them we've been using for a little bit, but we actually want to sit down and prove them and see where they come from. So first of all, I want to talk about how we can write groups. Can be written either additively or multiplicatively. And the important point here is that this is merely a notational difference. So we generally use one of 2 notations for the group operation. So if we write things additively, we'd write something like A plus B, where A and B are elements of the group. So that's for additively. And then multiplicatively, we write them as A times B. And we typically don't write anything next to it. We just concatenate the 2 symbols, and that means do the operation on those 2 elements. And as I said, this is merely a notational difference. We don't have to prove every theorem that we have twice, once for additive groups, once for multiplicative groups. They're all just groups. It's merely a notational thing. However, there is a fairly standard notational convention, usually when a group is written additively. The group is abelian. The reason for that is that in all of the examples that we're familiar with where it makes sense to add things, so for instance numbers or vectors or functions or things like this, addition is always commutative. A plus B always equals B plus A. And so typically we're going to reserve the notation addition for situations where the group is abelian. Multiplication, on the other hand, is sometimes commutative and sometimes not. So sometimes abelian and sometimes not. And this is because while some multiplications that we're familiar with are commutative, for instance, multiplication of real numbers, there are lots of types of multiplication, or things that can be interpreted as multiplication, which are not commutative. Matrix multiplication is the most natural thing to think of that way. Composition can be thought of as a sort of multiplication. It's also non-commutative. Or even the cross product of vectors. That could be understood as an algebraic operation of which is not commutative. And so when we write down a group, we should always specify. Never let the mere notation of the problem tell you whether something is abelian or not. However, typically, addition is only used for abelian groups and commutative operations. Now, because we've got these two different notations here, we have two different notations for what we mean when we apply the same operation more than once to the same object. So, on the additive side of things, if we want to write, say, a plus a plus a plus a plus blah 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 plus a, and let's say we have n copies of a, we're always just going to write that as n a. Now notice here, the way we've written it, n is an integer, and a is a group element. Normally this won't be a problem, but we should be careful about it when we go and look at these things. And similarly, if I have a whole bunch of inverses of a that are all being added together, we're going to write that as negative n times a. And again, negative n is the integer, a is the group element. And now when we have multiplication involved, and we've got a repeated multiplication, we're going to write that using exponential notation. So a times a times a, blah, blah, blah. N copies of that is a to the nth. And if I take a whole bunch of inverses of a and multiply them all together, that gives us a to the negative n. And the fact is that all of the facts that you know about in terms of factoring things on the additive side, or the rules for how exponents interact with each other on the multiplicative side, they all still hold, although they do need to be proved. I'll just mention that we set a to the 0th to be the identity. So it's an exercise to show that, for instance, if I have a to the m times a to the n, this is a to the m plus n. This is a little bit more tricky than it looks, because you do have to consider, well, what if one of these exponents is negative? And you have to consider a few different cases that way. But the point is that all those rules do in fact hold. And so from now on, we're going to use them without further comment. Now let's prove some theorems about the properties of groups that we've been using without mentioning. I've been talking about the identity of a group, or the inverse of an element, but technically it requires some work to prove that a group can't have more than one of either of those. So let's look at Theorem 24. A group G contains exactly one identity. Well, first of all, we know that G has at least one identity because it's a group, and that's part of the definition of the group. So we just have to show that it can't have two different ones. Or another way of saying that, we need to show that if two elements of G are the identity, or behave like an identity, then they have to be equal to each other. So we're going to do that here. So let's let E and E prime be identities for G. Now we have that E is equal to E prime. And why is this? This is since E prime is an identity. Since E prime is an identity, E prime times anything is that thing back. So in particular, E prime times E equals E. But we also know that E is an identity, which means that if I take E times E prime, I'm just going to get E prime back. So this is since E is an identity. Now, because equality is transitive, since E equals E prime, which equals E prime, this means that E has to equal E prime. And we're done. So not too difficult to show, just using the properties of what it means to be an identity. The next thing that we want is a property called cancellation, which is very important. So cancellation says that if AB equals AC, then then B equals C. And also if BA equals CA, then B equals C. So in other words, the first statement is saying that we can cancel things that both show up on the left side of an equation. So A is on the left of both those equations, we can drop them off. The second one says that if A is on the right side of both equations, we can drop them off. Note, this is not saying anything about the equation AB equals CA. In this case, this does not necessarily mean that B equals C. And that's because multiplication may not be commutative in our problem. So AB equals CA, Theorem 25 says nothing about this situation. And in general, B and C could be very, very, very different in a group, and we could still have that A times B is equal to C times A. Now the proof of Theorem 25 is pretty straightforward. If I have AB equals AC, I can let A inverse be an inverse of A. We haven't yet shown that A has a unique inverse, so we'll just let A in this notation, A inverse, stand for any of them. Just pick one. Now, if AB is equal to AC, then A inverse times AB certainly has to equal A inverse times AC. And now by associativity, we have that A inverse A times B is equal to A inverse A times C, which implies that the identity times B is the identity times C, because the inverse, or an inverse, of A has the property that if you multiply it by A, you get the identity. But the identity has the property that E times B is equal to B, and E times C is equal to C. So, basically what we did here is we multiplied by an inverse of A on the left of both sides of our equation, and we could do the same thing on the right. Though again, because the multiplication might not be commutative, we have to be very, very careful. We can multiply the same thing on the left of both sides of an equation, or multiply the same thing on the right of both sides of an equation, but we can't multiply one thing on the right and one thing on the left of an equation. Cancellation, Theorem 25, allows us to prove that inverses are unique, which we didn't actually need for Theorem 25. So Theorem 26 says inverses are unique. So let's let A be an element, and let's let B be an inverse of A. Again, since we're working in a group, A is guaranteed to have at least one such inverse, And in particular, this means that B times A is the identity and A times B is the identity. So now, let's suppose that B prime exists so that B prime times A is the identity. Then that means that B prime A is equal to BA, because B times A is the identity. So by cancellation, this means that B prime equals B. Similarly, if A times B double prime equals E, then A times B double prime equals AB. So again, by cancellation, B double prime equals B. So what this says is actually something slightly stronger than inverses are unique. It says that if B is any element such that B times A is the identity or A times B is the identity, then B has to equal A inverse, which is unique. In particular, this allows us to get a very convenient way to prove that one thing is the inverse of another. So to prove that x equals y inverse, for instance, for any x and any y in your group, it suffices to show that x times y is the identity, or indeed to show that y times x is the identity. So if you've got two things and you suspect that one is the inverse of the other, you can always prove that simply by multiplying them together and seeing, do we get the identity out of it or not? If so, then congratulations, you've proved that those two are inverses. And if you get something other than the identity, then in fact you've shown that they are not inverses of each other. One of the most important things that we need to worry about or remember when looking at groups is, of course, the possibility that they may not be abelian. And so, as a warning, related to the notations that we had before, in general, if I take a times b raised to the n, this is not equal to a to the n times b to the n. And that's because ab to the nth power is, by definition, ab times ab, all up here to ab, n times. Now, by associativity, we can drop the parentheses. The parentheses don't affect things, but we get ab, 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 dot, 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 up to ab. And if our group isn't abelian, we may not know any way of simplifying this. In fact, there are many groups in which a string of elements like a, b, a, b, a, b, etc. can't really be simplified. You just have to leave the element like that. Now, the good news is, if the group G is abelian, then we do have this, that ab to the n is equal to a to the n times b to the n. That's an easy exercise, which you can start with just the previous line involving what does ab to the n actually mean. But there is one power that we'd want to put up here in place of n that we work with enough that we want to make sure we handle correctly. So that's Theorem 27, which says that if I take two elements and I want to find the inverse of their product, what that is it's the product of their inverses, but in the other order. So if I take A times B, inverse that whole thing, then the result is B inverse times A inverse. Actually, we can get something more general than this. If I have like A1, A2, up to AM inverse, that's going to be AM inverse, AM minus 1 inverse, all the way down to A2 inverse, A1 inverse. So taking the inverse of a product is the same as taking the product of the inverses, but in reverse order. The proof for this is an exercise. But you should use this fact up here. If I want to show that B inverse A inverse is the inverse of AB, what I need to do is I need to multiply them together and show that I get the identity out of it. And if you can do that, then that's enough to prove that this B inverse A inverse over here is in fact the inverse of AB.